is Valeriano Villar, and I'm going to answer the question for the preliminary exam. So I have this solution, so let's watch this. Okay, so for problem number 1, the compression ratio of an air standard Otto cycle is 9.5. Prior to the isentropic compression process, the air is at 100 kilopascal, 35 degrees Celsius and 600 cubic centimeter. The temperature of the end of the isentropic expansion process is 800 Kelvin. Using the specific heat values at 100 at a room temperature, determine the highest temperature and pressure in the cycle. B. The amount of heat transferred in kilojoule. C. The thermal efficiency, and D. The mean effective pressure. So first, let's write first the diagram. So for PV diagram, the PV diagram for Otto cycle is like this one. First process, second process, third and fourth. So obviously this is the highest pressure, and this is also the highest temperature. So let's write the given. We have the compression ratio of 9.5. P1 is equals to 100 kilopascal. P1 is equals to 35 degrees Celsius, converting to Kelvin, 273.15. So our T1 is equals to 308.15 Kelvin. We also have our V1, 600 cubic centimeter, or that is 0.0006 cubic meter. Also, and temperature at the end of the isentropic expansion, 800 Kelvin. So let's find the highest temperature. So obviously we're going to find T3 and P3. So let's solve first for T2. For T2, we have the equation, the derived equation. D1 is equals to V1 over V2 raised to K minus 1. So this is the compression ratio, V1 minus V1 over V2. So substituting the value, 308.15 times 9.5 raised to 1.4 minus 1. So our T2 is equals to 758.3184 Kelvin. This is the T2. So let's solve for P2. So for P2, we have the derived equation from the isentropic process compression. We have V1 over V2 raised to K. So obviously this is the compression ratio. So substituting the value, our P1 is 100 kilopascal multiplied to RK 9.5 raised to K 1.4. So our P2 is now equal to 2337.806 kilopascal. So from this, let's jump to the process 3 to 4, isentropic expansion. So we have the formula T3 over T4 for isentropic is equal to V4 over V3 raised to K minus 1. but V4 over V3 is equals to RK. So from here we can get the value of T3. So our T3 is equals to our T4 800 Kelvin, 9.5 for the compression ratio raised to K minus 1. So our K is 1.4 minus 1. So our T3, which is the highest temperature, 1968.6995. So Kelvin. So this is our T3. So for P3, we have the from the process 2 to 3, which is constant volume, we have the derived equation P3 over P2 is equal to T2 is equal to P2 over P3 over P3 over T3 is equals to P2 over T2. So our T3 is equals to P3 T2 over P2. So substituting the value, we have our pressure P3 so the unknown is P3. So P3 is equals to P2 T3 over T2. Substituting the value, with the value of P2 of 2,337.83 multiplied to T3 1968.6995 over T2, which is 758.3184 Kelvin. So our P3 is 6069.3317 kilopascal, which is this is the highest pressure. So let's solve for B. So in B, we're going to determine the heat added. So we have the equation MCV. Heat added is T3 minus T2. So let's find M. We have the equation from the ideal gas equation, PV RT. So we have P1 100 kilopascal and our V 0.0006 cubic meter over R, which is constant 0.287, and T at D1. So our T1 is 308.15. So from here we can get the value of M 6.788 times 10 raised to negative 4 kilogram. So substituting the value, QA is equals to the M 6.788 times 10 raised to negative 4 kilogram multiplied to CV 0.7176. So this is kilojoule per kilogram Kelvin. And T3, we have T3 1968.6995 minus T2 758.3184. So from here cancel the values. We have the heat added is in kilojoule, 0.590 kilojoule. So this is for B. So for C, it's going to find the efficiency. We have the equation 1 minus heat rejected over heat added. So okay, so let's find heat rejected. So QR is equals to MCV T1 minus T4. So substituting the value, we have 6.788 times 10 raised to negative 4 for mass, and CV 0.7176 kilojoule per kilogram Kelvin, and we have our T1 308.15, and T4, for T4 we have T4 we have 8,800 Kelvin. So let's solve. We have the heat rejected of 0.240 kilojoule. So this is negative because it is heat rejected. So from here we can solve the efficiency. 1 minus QR, our QR is 0.240, okay, over QA 0.5 QA 90 kilowatt, because kilojoule per seconds is kilowatt. I forgot to write, this is kilojoule per seconds. I know this is only kilojoule. Okay, kilojoule. So for the efficiency, we have 0.594, or multiplying by 100, our efficiency is equals to 59.4%. So for the mean effective pressure, we have the equation work net over volume displaced. So volume displaced is equals to V1 minus V2. Okay, so our V2 is equals to V1 over DRK. So substituting the value, we have the work net. Work net is QA minus QR. We have QA of 0.590 minus QR 0.240 over the volume displaced, V1 0.0006 minus V2 0.0006 over RK 9.5 is now equal to, the mean effective pressure is now equal to 652 kilopascal. Okay, so for cut-off ratio, so what is cut-off ratio? So the cut-off ratio of the volume, the cut-off ratio is the ratio of the volume after the combustion to the volume before combustion. So we have the equation for the thermal efficiency, 1 minus 1 over RK raised to K minus 1, multiply it to the RC raised to K minus 1 over K times RC minus 1. So from this equation, RC is equals to the cut-off ratio. So for RK, this is the compression ratio. So the effect in the cycle is it is observed that the thermal efficiency of a diesel engine can be increased by decreasing the compression ratio, cut-off ratio, or by decreasing the value of K. So by decreasing the value of by decreasing the value of this equation, it is nearly to 1. So let's say if you increase this value, 1 minus, let's have for example 1 minus, we have 0.5. So if we decrease this value, let's say 1 minus 0.4, the difference is your thermal efficiency from the original 0.5 is 0.5, or that is 50%. If we decrease the value of compression ratio, cut-off ratio, or decay of the gas, for example, we decrease from 0.5 to 0.4, we can get a value greater. So 1 minus 0.4 is 0.6. So we have 60% thermal efficiency. So it is very efficient. So by decreasing this value, the effect to thermal efficiency is increasing. So they are inversely proportional. Okay, so that is the explanation.